Hi everyone. In this video session, I'm just going to discuss one of the very important question. In fact, it was very good question also. That checks, or you can say that is going to examine your basic understanding about Zener diode as well as the RC circuit. Okay, and this RC circuit was a very particular RC circuit where the no external sources are given to excite the network. Only RC circuit is given, and across the capacitor there is an initial voltage, right? So it is one of the very easiest circuit, right? If you have been given a source free RC circuit, certainly your capacitor will discharge. It is not going to further charge. Okay, whatever voltage across the capacitor is there, that will remain same. Okay, it is going to discharge, okay, after the switch is closed. That is the idea behind that. Okay, if switch is not closed, okay, switch is open, so whatever voltage across the capacitor is there, that is gonna be same. And there are many ways to solve this question, so I'm just going to discuss some of the important ways, and you have to take whatever ways you like. Okay, so let's move to solve this question. So as you can see, this question was 2 mark, okay, from the network theory. And again, you see this question was asked as NET type. So almost all the questions from network theory, 10 mark, 10 mark question. You can say 5 questions were there, right? And all 5 questions were numerical answer type. Okay. So let us solve this question. So as shown in the figure, okay, as shown in the circuit, the initial voltage across the capacitor is given. Yeah. Certainly, if it is a source free circuit, how to identify it is a source free circuit? Because there is no external sources. Okay, if there is no external source which can excite the network, RC circuit, RC network, so that that is considered to be source free circuit. Okay, there is no source at all. So if it is a source free circuit, then there should be initial voltage across the capacitor. Understand? And with the switch being open, so this switch is open already, right? Now the switch is closed at t equal to 0. The total energy dissipated we have to find in the Zener diode. Okay, and Vz is 5 volt after the switch is closed. Okay, the moment switch is closed, okay, we have to find the total energy dissipated in the ideal Zener diode. Okay, and we have to find the energy in millijoule. Okay, and up to 3 decimal places. Up to 3 decimal places, that is important to remember. Okay, up to 3 decimal places. Okay, so up to 3 decimal places, suppose you are getting 2 decimal place also, so you can attach 0. That will be the correct answer. Fine, let's move ahead. So let us solve this circuit. So what are the observations that we can make from this circuit, right? First of all, this circuit is a source free circuit. Source free circuit. Okay, as no external, you can say that sources are connected. Okay, that is the first observation that you have to make. Okay, now the second point is, if this is a source free circuit, or sometimes we call it SFC, so you should understand that the moment the switch is closed, right, okay, this capacitor will start discharging. Okay, the capacitor is going to discharge. Understand, the capacitor is going to discharge. Okay, that is very important. Okay, now how, when the capacitor discharge or when the capacitor charge, you should know that capacitor charges when the current flows in the capacitor, or capacitor discharges when current flow, you can say current is gonna flow. Okay, so current has to flow here. If current is flowing, remember, okay, so the moment the switch is closed, right, the current will start flowing, okay, toward the resistor. Understand, like this. And this is a path the capacitor is gonna find. Okay, so capacitor will start discharging. Okay, I think this is clear. So this current is going to be what? And as we know that we can model it. Okay, so the current which is going to flow, okay, in this direction is going to be consider as the Zener current also, right? So this Zener current is going to be what? You can say that 10 minus, or you can say that simple, this you can take as a this current also, okay, the capacitor current, okay. So this capacitor current is going to be what? I naught e raised to power t by tau, okay. So I naught is going to be what? I naught will be 10 minus 5 by 10 k, okay, because the difference, the moment switch is closed, your Zener diode is going to be on, okay. Zener diode will be in breakdown. How to say Zener diode is in breakdown? You should know this background also related to Zener diode. See, suppose this is Zener diode. This is going to be Zener diode. If it is in breakdown, so you have to replace it by battery of, you can say, VZ. If it is in breakdown, okay. And Zener diode works in reverse direction, reverse bias, you can say. And if it is not in breakdown, you have to replace it by open circuit, right? If not in breakdown. Now, how to determine whether it is breakdown or not? Whether it is in breakdown. So, if the voltage across this is VZ. Okay. So what I was telling here is Zener diode कब breakdown में होता है, कब breakdown में नहीं होता है. If it is in breakdown, remember, if it is in breakdown, okay, so it will be replaced by battery, and battery has to be, polarity will be plus to minus like this, okay. And if it is not in breakdown, okay, Zener diode is not in breakdown, so you have to replace it by open circuit, simple, right, like open circuit, understand. Now the question is when the Zener diode is going to be breakdown. Remember that suppose this is a Zener diode, okay? This is a Zener diode, right? And if suppose the Zener diode voltage, the breakdown voltage is nothing but VZ, and if you are applying here some sort of Vx, okay, some voltage you are applying. So when this guy will be in Zener breakdown, okay, when Zener diode is going to be in breakdown, okay. Zener diode is in breakdown, okay. So you can say that when Vx is greater than Vz, when Vx will be greater than Vz, okay, so that Vx in that circuit is nothing but the initial voltage across the capacitor, that is greater 10 greater than 5, so certainly it is going to be on. So if it is this, so equivalent you have to draw is like a battery. So your battery will be replaced by, Zener diode will be replaced by the VZ, okay. And let's say the situation is, this is a case 1, you can say case 1. And the case 2, okay, these things we discuss in analog circuit, okay, most of the time, right? Not in a network theory we discuss, but they have considered, okay, this question, they have included Zener diode along with the RC circuit, so no problem is there. So now if suppose this Vx is less than Vz, not in breakdown, right, not in breakdown, so you have to simply replace the Zener diode by open circuit, so current is going to be 0, right? Now the question is what will be the maximum power dissipation? I think everybody knows the maximum power dissipation, right, that the Zener diode can have, right, is nothing but the maximum power dissipation, you can say Pz max is going to be the voltage Vz, which is constant, and here Iz max, okay. Now how to compute energy from the power? Everybody knows, right, how to compute energy from the power. So energy from the power is basically energy is equal to P dt, okay, P dt. Okay, so you have to integrate power, okay, and power is nothing but voltage times the current, right? Voltage times the current. So what is the Zener current that is flowing through the circuit? That is very important to remember, right? So you can see here what I'm trying to convey here is this is a current, okay, this is going to be a Zener current only, right? This is a method one I'm telling you, right? Remember, this is method one, where you have to remember that whenever the source free circuit is given, right? So the current equation is going to be like this, okay? And this will be the Zener current only, right? So you can say that this is going to be 10 minus 5 by 10, right? So 10 minus 5 by 10 k e raised to power t by, what is tau? Tau is the time constant. So tau is going to be, 10 into 10 raised to power minus 6 RC, R is this. So at this moment, I'm not using any sort of intuition. Remember, I'm just using, solving question, okay, with the help of many steps. Though this current equation we have got by inspection, but if you are going to derive it, then it will take further steps, okay? So many students are like, they will first find out the voltage across the capacitor, then they will differentiate it to get the current, then life is very tough, right? But you should understand this, okay? The second approach you will like certainly, ठीक है? Second approach आपको पसंद आएगा. इस approach में थोड़ा सा आपको tedious लग रहा होगा, right? I don't like this approach also. Simple, but it's okay. So you see, guys, this tau is going to be what? 100 into this, it means this is 100 into 10 raised to minus 3, which is 0.1. So your tau is 0.1, right? Now this current is going to flow. Okay, this is a decaying current going to flow through this VZ, right? Okay, like through Zener diode. Okay, so you can simply put in this equation. So you are going to find the total energy from 0 to infinity, you can say, and this is going to be this is phi, okay, that is Vz times the current is nothing but what is current here? Let me check the current. Okay, this is 0.5 milli, okay, 0.5 milli, okay, ampere e raised to power minus t by 0.1 dt. Now you can take this, whatever constant is common, so you can take it out. So it is 0. It becomes what? You can say that 5 into 2.5 means 2.5 milliampere, okay, into 0 to infinity e raised to power minus t by 0.1 dt. So guys, what is going to be, if you're going to integrate this, you should know that integration 0 to infinity e raised to power minus at dt is going to be erased, it is going to be 1 by a only, right? In signal and system, you have studied these things, yeah? So directly you can write this as 2.5 into it is going to be 0.1 millijoule, which is 0.25 millijoule. The answer for this question is 0.25 millijoule, right? This is one approach, okay? So answer for this question is nothing but 2.5 millijoule, but answer has to be written in 0.25, okay, because they are asking. But answer आपको पूरा लिखना है. up to 3 decimal का मतलब क्या है? 0.250. Okay, this is the answer, okay? So what are the things that I have done, right? आपको सबसे पहले तो you have to make observation whether it is a source free circuit, right? Then this current equation, right? And then life is simple. This is a decaying transient situation, okay? And how to find the time constant and all, right? And the background related to Zener diode, it's a very simple, I think I have taught in analog circuit, so you should understand that. Okay. The approach number 2 is what? I like the approach number 2, guys. The approach number 2 is very interesting approach, right? Let me solve the question using approach number 2. I hope you will enjoy that. Okay. Yes. So the same situation, right? And we have to solve it, right? So you know that when the Zener diode is gonna be on, right? Zener diode is going to be on So the your PZ, that is Zener diode power dissipation, is nothing but VZ times IZ max, right? And total energy dissipated you have to find. So what we can do here is, you can say energy is gonna be PDT, right? That is VI, okay, VZI times dt, right? VZI times dt. We don't know this current at this moment, right? Okay, so what, and this VZ is constant, you can say. So you can say energy is going to be VZ is out, and you can say 0 to infinity IZ, I mean IZ dt. So guys, can you recall what is this? What is this? You can understand that this is nothing but your charge. Yes, this is nothing but a charge, all right? Charge क्या होता है? Charge is nothing but what? How current is related with the charge. Area under the current, okay? You can say that area under the current is equal to charge. But here you see, we have to see this charge. We have to consider the initial charge and the final charge, right? And we have to subtract it, right? So this energy, the total energy which we have to find, okay, that is going to get dissipated in the Zener diode is going to be VZ times, okay, the initial charge, okay, that is final charge minus initial charge, Q final minus Q initial, right? This is what the answer is, where you don't have to compute integration at all. In fact, you don't have to compute time constant and anything. ये भी एक बहुत अच्छा अप्रोच है, ठीक है? So what is the, so this is nothing but VZ times the change in charge, okay, change in charge. What is change in charge, guys? Change in charge means the final charge minus initial charge, okay, understand? So but you have to take this as energy has to be positive, so take it like modulus of this, mod of that, okay, because the energy has to be positive, okay. So VZ is nothing but 5 volt into, what is final and what is initial? So can somebody tell me what is initial charge from here? So you can find out the initial charge is gonna be what is initial charge? You see, the initial voltage is 10 volt and the capacitor is this, right? So Q equal to CV, right? Q equal to CV. So this is 10 into 10 to the power minus 6, 10, that gives you 100 millicoulomb, right? Initial charge. And then the final charge is going to be how much? Final charge means the final voltage. The final voltage is going to be what? What is final voltage? That is 10 minus 5. That is 5. So you can say that capacitor is same, okay, and this is 5, which is 50 millicoulomb. So how much charge that Zener diode is going to take, okay, from the capacitor? Effective is nothing but 50 millijoule. Okay, the change is 50 millijoule, okay. So 5 into 50 milli, so not 50 millijoule, sorry, 50 millicoulomb we should say, not joule. Okay, so this becomes 50 millicoulomb. Voltage times the coulomb, right? That is gonna be given the joule. So this is nothing but 250 milli. Okay. I believe this is yes. So 1 minute. I think we have done some sort of error, or what answer is? Just wait and watch what is happening here is yes. You should write micro, guys. Sorry, I must consider this is micro only. I have done mistake here in unit. ये माइक्रो कूलॉम में ही रहेगा, ठीक है. So this guy should be in micro coulomb. Okay, so this is in microcoulomb, please remember, okay, 50 microcoulomb. So this is 250 microcoulomb, but answer has to be written in microjoule. This is in milli, will 0.25, 0.250, oh sorry, milli, joule. So it's a very simple answer that we have got, right? Okay. So see, I have explained this question for 20 minutes and I've given you background as well, right? So you have to learn from this question. ठीक है, आपको ये सीखना पड़ेगा. Okay, I think this is clear. देखो, whenever source free circuit is given, remember, whenever source free circuit is given, suppose this is a capacitor and there is a resistance R and this is capacitor. Certainly they will mention the VC0 minus. The initial voltage they will always mention, remember, okay? So you should know that what is the VCT here. That is going to be VC0 minus e raised to power t by tau. And where tau is going to be RC, guys. Okay. And you can also find the current here, right? So current is going to be what? ICT, which is C dVc by dt, right? Okay, so you can differentiate this guy, right? So it's a very simple procedure, right? So at the end of the day, you will find ICT also in terms of I naught e raised to power t by tau. Right? Simple it is, right? Whatever voltage is there, this is the initial current, right? So initial current will flow, right? Like this, okay? So that current is going to be, इस current को आप direct find कर सकते हैं. Instead of differentiating, right, needless to differentiate, you can directly write VC0 minus by R e raised to power t by tau. Okay, it will always decay only. Your capsule is gonna discharge. It is a discharging, transient situation. Okay, discharging transient situations. Okay, so you have to find in this question, you had to find the energy dissipated by the Zener diode. So that was very easy, right? Power integration, yaki charge. Okay, how much the total change of charge, like how much charge you need, okay, from the capsule. So you're going to take the charge from the capsule. So there was initial charge 100 milli, and you have taken 50, not 100, you can say, yeah, 100 micro or something. Yeah, micro was there, right? 100 micro, and you have taken out 50 micro, right? So 50 times 5 is the correct answer. So आपको notice करना है कि area under the current I dt, okay, I dt is nothing but change in charge, okay, I dt. और एक और ये भी याद रखना है कि इक्वल टू CV होता है. ये सारे इक्वेशंस आपको पता होने चाहिए, ठीक है? और बहुत सारी चीजें हैं जो आपको समझना है, राइट? यू हैव टू टेक केयर ऑफ यूनिट्स, माइक्रो, मिली, kilo, all these units you have to take care of, right? So it's a very simple question. So I have done all 10 questions, okay. I think you might have seen कि all were easy question. बस यही एक question था, काफी interesting था.